Yeah, welcome everyone. It's fantastic, to have this workshop focused on unconventional superconductivity. And this activity actually arises from a recent discovery of nuclear superconductors and many recent progress on cuprates, as well as iron-based superconductors. So we thought we'd get experts around the world to have this sort of a small online workshop to discuss the latest advances. So for the first speaker, we're happy to have Stephen Hayden from University of Bristol talk about his very interesting measurement on spin fluctuations in the normal state of superconductors. And this work is published in Nature Physics not very long ago. Okay, yeah, thank you, Stephen. It's all yours.
Okay, thank you, Peng Chen. It's an honor to be the first speaker at this symposium. And I'm going, as Peng Chen said, I'm going to talk about spin fluctuations in the normal state of cuprate superconductors. So let me just start by showing my my collaborators here. So the work that I'll be showing mostly is from the paper in Nature Physics, and Mengji Zhu was the postdoc who did that, and I'll also show a little bit of new data from Jacopo Rodelli. And these are the other people involved in the work. Just to put things in context, I'm just going to show a little bit of strontium muthinate, and some of these collaborators have worked on that. So here are the papers, and here's a recent review at which some of the things will mentioned were in, and I just thought I'd mention that. So let's go on. So I'm just going to focus on one particular point here, which is the purpose of this work. Of course, there's lots of work measuring spin fluctuations in the cuprates, and the I guess the work is over a wide energy range, going up to the energies of the spin waves in the parent compounds, and I think a lot of work concentrated at low temperatures, particularly on the superconducting state. And in recent years, we've realized that the normal state is very anomalous in cuprates. So we went back and revisited the normal state, particularly around TC, to find some very low energy spin fluctuations, and that's what I'm going to talk about today. So a little bit about strange metal behavior. This is seen in the most clearly in the overdoped region of the superconducting phase diagram. So here we've got LUSCO, and what do we mean by the strange metal behavior? Well, of course, linear T resistivity is known for a long time in cuprates, and that's the primary thing. I guess in recent years it's been shown that it continues down to very low temperature, and you can see when you remove the superconductivity of the magnetic field that it's still linear behavior. And the other aspect to it, which I'm not going to show much data about, is the specific heat. In general, people taking things beyond the cuprates, when people talk about strange metal behavior, they often also have unusual behavior in specific heat with T log T terms, for example, upturns at low temperature and particularly large specific heats. So here's some paper from Nigel Hussey, who's going to be talking tomorrow. This is an old paper in Science which shows the linear resistivity in LUSCO, and how it varies across the phase diagram, and you can see in this region here how linear it is. If you go to higher doping, it starts to look curve more T squared. And of course, for the underdoped region, you get the pseudo gap. So the sample that we particularly studied was somewhere between 0.1, between 21% and 23%. So we'd expect it to have a nice linear resistivity. Here's something that I guess doesn't get shown quite as much in talks and so on. There's a specific heat of LUSCO, pure LUSCO. There's two sets of data I've got here. This is some old data from John Loram, 2001. And he has a technique which allows him to go to quite high temperatures by subtracting the background directly during the experiment by doing a differential measurement. And you can see this purple line here is the specific heat for the sample that I'm going to be talking about today, or a sample with the same composition. And you can see it's got an upturn. It's also got quite a high specific heat as you enter the superconducting state here. The specific heat that John Loram quotes his data in is in very strange units per gram atom here. So, but they are consistent with other people's data. He divides by the number of atoms in the unit cell, as people used to do so. Here's some other data just to show that this is consistent with this data. This is from a Japanese group, and you can see, for example, a 0.22 is actually in this inset here, and there's quite a large specific heat at TC. So we have about 15 millijoules per Kelvin squared if you take the linear gamma, so C divided by T. Okay, so if you collect together specific heat data and you look at what gamma is as you vary doping, you can see there's a nice peak here around about 0.22 where the sample is. So it's got a relatively large linear specific heat. So what I'd like to try and convince you today is that the spin fluctuations may be important to understanding this last specific heat, and also the linear behavior in the resistivity. Just before I go on to talk about the LUSCO, though, let me just show another material which has a clear connection between the low energy spin excitations and a linear specific heat. This is the bilayer ruthenate material, strontium-3, ruthenium-207, popularized by Yoshimino and Andrew Mackenzie. And of course, this is an entropy diagram showing derived from the specific heat, showing this that there's something a quantum critical like point appearing as you change the magnetic field. Anyway, here we've got the resistivity plotted for different magnetic fields, and one can see that at high fields, at the point where you get to this this thing that looks like a quantum critical point and beyond, you get a very nice linear specific heat. And at low fields, it's more curved around with temperature. So the linear part is strongest in the right-hand side of this phase diagram here. If you go to higher temperatures in strontium ruthenate, also the linear behavior actually goes on for a long time, just like in the cuprates. As you can see here, this is in zero field. This paper actually, from which these curves are derived, is this a famous paper from Andy Mackenzie's group, and he showed that actually for a wide variety of systems, you could relate the scattering rate that comes out from a sort of Drude model for this resistivity to the temperature, and he found that they're similar if you compare different systems. This line here corresponds to these things being equal, and you can see strontium ruthenate is close to this line, and also this cuprate material he put on here, the 2212, is on the line. So I'll come back to that later on. This is the so-called Planckian dissipation. So anyway, just on strontium ruthenate, the connection with the spin fluctuations. Here we've got the measured spin fluctuations in strontium ruthenate measured on LET, and you can see here 2 points in reciprocal space where the strong low energy spin fluctuations. The energy scale of these spin fluctuations varies as you change the field. And you can see here at low fields, they're kind of out of the window of the experiment, which goes up to about 1 millivolt here. And as we go through that, the quantum critical point into higher fields, we get these very low energy spin fluctuations, the gray regions here. So this is the spectra measured at the incommensurate position here. So in the presence, when these spin fluctuations are there, the low energy ones, we find that actually the low temperature resistivity becomes linear here quite dramatically. So you can compare the susceptibility that comes out while fitting this low energy contribution to the spin fluctuations. This is the susceptibility pole. Chi, the real part of susceptibility, and you can see that gets larger as we go across, as you might expect. Okay, so that's just to show you that there are systems, also heavy filament systems as well, where the presence of low energy spin fluctuations goes hand in hand with linear resistivities, particularly at the lowest temperatures. So the question is there something similar happening in the cuprates? So just to put things in context, because there's many papers on the spin fluctuations in LUSCO, I've made a schematic here to try and show you how what I'm going to show you today relates to all the other spin fluctuations. So this is just a schematic for LUSCO showing what happens if you kind of go through reciprocal space and just plot out schematically the spin fluctuation spectrum. And so if we go along this line here, and then along here through these red dots, which correspond to the points of reciprocal space where you get the lowest energy spin fluctuations, that corresponds to be going along this line on the bottom here. So one gets a sort of broad, these excitations here going up to about 300 millivolts in dope materials. These are seen in RICS, and then a neutron scattering measures around a half or pi, where the excitations become stronger and they dip down again. And we have a lot of spectral weight here, which we believe might cause a pairing. We have the so-called hourglass. And there's, I'll show you in a minute, there's some stuff that is peaked around about 50 millivolts. If we just look at this region here, and then there's another contribution which goes down to the lowest temperatures here, sorry, the lowest energies here, which is what I'm going to talk about today. So it's this little blob on the end of the tail. So here's some rare data just to show that. With RICS, we can see these broad things. And then as you come down in energy, we see scattering near pi or half. These maps here, the center of these maps is a half. So this is at 150 millivolts, and we drop down to say about 50 millivolts, where we see this sort of peak at about 50 millivolts is a strong blob at pi, and then below 50 millivolts there's another contribution, which you can see down here, and these four peaks which was observed in the early years after high temperature superconductivity was discovered. Anyway, so actually all this data here we took in the superconducting state. So in some sense we've gone back to revisit this and measure at low energies. This is the spectrum of the whole thing, just around half for different dopings. So you can see these three contributions. This is the sort of high energy spin waves, the blue, and then this peak here is the incommensurate peaks that I just showed you, which you see for many dopings. And then for some dopings, you also see spin freezing for the underdoped side, and that's the pink stuff here. So this peak here is the incommensurate peaks at low energy. You can see it has, these are all measured in the superconducting state. So actually it pushes the spectral weight up above the gap, and you see a so-called resonance. But you can see it occurs across here. So this is the old data we had on over a much bigger energy range. We're going to now look at this thing here in detail this plot actually here you see is actually in the superconducting state, so it's quite strongly peaked. Okay, so the sample I'm going to talk about is here. And just to put things in context, I'll show you some older data which we took a long time ago. So when I was working with Gabe Apley and others, and this is actually a sample here in the underdoped region. So in the underdoped region here, we found incommensurate peaks, and here you see different temperatures, what the response looks like, and you can see it's strongly temperature dependent. This one here is at 300, no, about 300K, and then this one here is at about 35K. So this one's actually about TC. So on the underdoped side, then, if we were to read off an energy scale here, we'd say it's about 10 millivolts. So that's going to be higher than what I'm going to show you in a minute. I suspect now, looking back on it, that this, what appears to be a high energy scale, is actually due to the pseudo gap pushing spectral weight up from low frequencies. In fact, and that's why we see this. Okay, so that's the on the underdoped side. Now let's go to our new data on the overdoped side, and here we have this data on LET. We can go down to very low energies, and here you see data taken for different temperatures and fields. This is the data taken in the normal state, and you can see these 4 peaks in the response at very well developed here at an energy of about 1.2 millivolts, and then as you go up, things broaden out and it starts to get a little bit weaker. So if we just home in on one of these peaks, this peak here, and plot the data as a function of energy, this is the spectrum we get, and you can see there's a lot of spectral weight, and the characteristic energy scale that we could read off this is about 4 or 5 millivolts. So we can fit it. Actually, it fits very nicely to an overdamped harmonic oscillator, a very overdamped harmonic oscillator that is a Lorentzian function, and we find about the energy scale is less than 5 millivolts, so much less than, a factor of 2 less than the overdoped side, the underdoped side of the phasors. Okay, so the interesting thing about this is, if you compare this is the main result of the work then, if you compare this with temperature, this number here, the relaxation rate of the spin fluctuations is actually quite similar at a temperature, well, within a factor of 2. So it may have something to do with the with this Planckian dissipation and so on. If we we can do just two interesting things here. We can go into the superconducting state first of all. So this is in the normal state, just cool down, and if we go into the superconducting state without a magnetic field, we get these blue points here. Okay, and you can see there's an increase in the response here at higher energies. This red dotted line is what you have in the normal state. So this is like the resonance that's been seen in IPCO and in LUSCO. So this is an increase in response at higher energies, and you've got down here a suppression due to the superconducting gap. Now, if we suppress the superconductivity with a magnetic field, we've only got a pretty small magnetic field, about 8.8 Tesla here. You can see that the response actually, if we compare with what was at the normal state, is actually much is increased. So this suggests that the system, if we, if the superconductivity didn't intervene, would continue to have these low energy spin fluctuations. In fact, they'd become even lower energy. One can think of this green curve actually as a superposition of the normal cores and superconducting the rest of the material. So this is a mixed state, of course, and the response with shear neutron scattering should be a superposition of two responses. So this low energy bit here actually is only coming from part of the sample. So if we were to home in and do the experiment just on that part, this would even be a stronger and possibly even a lower energy scale than we see here. So anyway, I've tried to illustrate this schematically, that this sample here is sort of heading for some underlying hidden quantum critical point, if you like, but it doesn't get there because the superconductivity cuts off. But if you put a magnetic field on, so if you were able to put a big enough field on and do neutron scattering here, you would see presumably lots of even stronger spin fluctuations. That picture is supported actually by heat capacity measurements from Giraud and co-workers, and they show that the linear specific heat here, this is this curve here, increases with field as at low temperatures for pure LUSCO. Okay, I can see that I better finish up here. So we can parameterize the scattering with a Minus-Moulin and Pines type function. And here we've done that. There's some interesting parameters. We can get a correlation length basically out of the parameterization, and the energy scale, of course. And we find actually interestingly that the correlation length decreases as we increase P. This is 1 over the correlation length, so that increases between our two samples. So it seems that this isn't really described by a sort of quantum criticality to try and describe the whole thing, because as we go across here, as the the correlation length becomes shorter, the energy scale goes down. And I think that reason for that is probably what I said earlier on, that the pseudo gap is cutting off, is coming in on this side, and perhaps causing the energy scale to appear to increase. The other thing I'd just like to briefly mention, people ask me about this, these fluctuations that we're measuring here are much bigger than the ordered moment that's seen in underdoped LUSCO, for example. We see spin freezing and so on. So if you work out the moment that you get when you get spin freezing, it's about 0.03 Bohr magnetons per atom. So if you square that up, you can compare it with these fluctuating moments that we see in the dynamics. Of course, when we integrate, we end up with a moment squared in the fluctuating case. So this is much bigger than the spin freezing moment. So it's not that we're seeing in these experiments. Finally, we can make a rough estimate of the spin fluctuation contribution to specific heat using paramagnon theory based on the parameters that we find. If we go back to these papers from Longsovich and Moria and Brinkman and Engelsberg, basically by averaging the relaxation rate over the Boulogne zone. And this is the curve I showed you at the beginning, and these are the points that the spin fluctuation theory would give you based on our parameters, suggesting that you can understand this large specific heat in terms of spin fluctuations coupled to the conduction electrons. If we change the temperature now on this sample, this is some unpublished data, so newer data, that we can see that the energy scale of the spin fluctuation seems to change, and the strength of the chi changes very rapidly with temperature. So this top one here is the lowest temperature, and it's similar to what we see with the underdoped samples. These spin fluctuations are strongly temperature dependent, up to 155 Kelvin we've got here. So the two conclusions we've got are that there are low energy spin fluctuations coexisting with this strange metal behavior. We find that the relaxation rate of these spin fluctuations is close to the temperature, within a factor 2. The correlation length of these spin fluctuations is about 20 angstroms, and it may increase as we go into, if we were able to do the experiments under higher magnetic fields. And I said I've already given the conclusions for the strontium luthenate, so I'll stop there and thank you for your attention.
Yeah, thank you, Stephen. Yeah, very nice talk. So I mean, any questions? Maybe I can start with the question. So actually, can you go back a couple of slides in your slide? Actually, I sort of didn't pay attention. Can you go back one more or two more? The field dependence and temperature dependence. It seems like the field actually, when you try to suppress superconductivity, the field actually enhances spin fluctuation compared with the normal state. Yeah.
Yes.
This figure. Yeah, what's the reason for that? Yeah, I also, this is actually somewhat shocking to me. Yeah, I mean, I thought you would just basically recover, right? Why would the field induced spin fluctuations actually larger than that of the normal state? What is the reason for that?
Well, to me it suggests that as you're lowering the temperature, the spin fluctuations are getting stronger.
Mm-hmm.
Well, if you take out the temperature factor and plot susceptibility, that's getting larger as you lower the temperature, right? But when you get to the superconducting state, then there's a suppression. So when you put the field on again, you remove the superconductivity, and you see what you would have seen if superconductivity hadn't intervened. So it's as if you're heading to a quantum critical point or something that's related to the spin fluctuations. So they're getting stronger as you can see that also in the final one here. So if I go to this one, sorry, I flashed that a bit quickly. So here, this is the highest temperature here, right? Then we go to this one and to this one. Okay, so what we're doing now, it's as if we'll lower the temperature a bit more. So if the superconductivity hadn't intervened, it would be even steeper. But we never see that until we put the field on.
Okay. Subir?
Yeah, hi, Stephen. I wanted to ask about the total moment that you mentioned. So you said that the overdope side is a much stronger, this is like the third column. No, the last column. Yeah.
The last column.
The B squared is a lot larger now, but on the underdope side, are you integrating over the same frequency regime or what? That also seems rather surprising.
Yeah, what we've done there is to just integrate, basically to integrate up to 10 millivolts, right?
Okay, both the underdoped and overdoped.
Yeah, exactly. Yeah, and that, as I said at the beginning, this is only part of the susceptibility, right? It's just a little, the foot on the end of the body or whatever. There's like a response that looks like a damped harmonic oscillator on the end of it, and so it's that part that these numbers refer to, and you can see. Interesting just to compare the two samples. So this is the old sample from the old scaling paper from 2000, around about 2000, just before.
So does this suggest that there's a spin gap? At least part of the spectrum has been gapped out on the underdoped side. Is that what you're implying?
That's what I would.
Yeah.
That's what I would contend. Yes, or at least the pseudo gap has kind of pushed the spectral weight up. It's not like it's been lost. It's just been pushed up to higher energies, because this number is still bigger, the underdoped one, than this one. So, but they're comparable,
All right,
obviously.
thanks.
Chimel?
Nice, Steven. Nice talk. So I want to ask you about this last slide you had, the higher temperature data. Does the statement that the fit relaxation rate being roughly 2 times of kBT, does that apply to all these 3 temperatures you are showing here?
Yes.
Okay.
Sorry, that's a very direct question, and that's yes.
Yeah.
It does. Yeah.
Okay, good. Thanks.
Any other questions for Stephen? I mean, what's the range of temperature, Stephen, that the stability actually changes when you go cross TC? I mean, it seems like quite a big range, right? Because TC is rather low, right? Yeah, I mean, see, it goes to up to like 10 millivolt. You see clear changes, right? Well, what is TC? I mean, TC is like what? I mean, 10K?
For this sample,
yeah,
I think, sorry, I haven't got that on the tip of my tongue. I think it's 24K, 24,
yeah, 24K,
25.
24K is like, okay, 24K is like
25K.
only 2-3 mil. I mean, okay. So you
Yeah.
can see up to 10 millivolt, you can clearly see changes. That's somewhat surprising, yeah.
Yeah. Well, I guess it's the same in IBCO, right? You see changes up to 40
Yeah, five
millivolts.
times,
So,
yeah, 5 times kBTC. Yeah.
yeah.
Okay. Yeah. Okay. Yeah. Yeah. Thank you very much, Stephen. Yeah. Exactly on time.